Alright guys, so for today's lesson, starting in chapter 2, we're going to start talking about how we describe locations in a distribution. So we have 3 goals today: to be able to explain the characteristics and importance of a normal distribution, to explain the purpose of standardizing, and then to be able to calculate and interpret a z-score. So as we work through this lesson, I want you to be thinking about how you can explain in your own words the purpose of standardizing, and then to give an example of when I might need to standardize. So by the end of this lesson, you need to be able to answer these 4 questions on your prove-its. So look them over for a minute. Alright, so when I took the ACT and the SAT back way back, I got a 26 on the ACT and a 1610 on the SAT. So the question is, which test did I do better on? So I want you to think about that. What other information might I need to know in order to compare which test I did better on? So we have 5 vocabulary words that you need to become really familiar with for this lesson. We're going to be talking about density curves and specifically normal distribution density curves. We're going to talk about percentile, standardizing, and z-score. So be looking for those vocab words throughout this lesson. So these are just examples of different types of density curves you might see. So my first one is a uniform distribution, and the second one is bimodal. We have skewed left, we have skewed right, and then we have roughly symmetric, which is these 3 different ones. It's just showing different ways that that same roughly symmetric curve could look. So there's 2 rules for a density curve. One is that it's always on or above the horizontal axis. So none of my data ever goes below that horizontal axis. And 2 is it always has an area of exactly 1. So 100% of my data fits underneath that density curve. That's what a 1 means, 100%. And it just comes in different shapes and sizes, as you can see on here. We are going to focus specifically on the normal curve or the roughly symmetric one, but I wanted you to see the different shapes that can be. Alright, so the bell curve is also known as a normal distribution, and that is the one that we refer to as roughly symmetric. It is a normal density curve that is symmetric, is single-peaked, and is bell-shaped. So if you hear normal distribution or bell curve, those mean the same thing. One of the biggest things you need to be able to know is the notation. If I see an N, capital N with parentheses, and then I have a number, comma, another number, that's going to mean a normal distribution. The first number is the mean, or mu, that Greek letter mu that we use for mean, and the second number is sigma, which is the Greek letter for standard deviation. So that's what these mean. The normal distribution is really important in statistics. It doesn't always happen, so when it does, we like to capitalize on it. So a normal distribution allows us to convert between raw data and percentiles in order to draw conclusions about the data. So if you notice, we've taken this histogram and we've given it a bell curve by drawing that roughly symmetric bell curve over it. And we've said this is a normal distribution. So we're going to look more at what that looks like and what it means, but I just need you to know it doesn't happen all the time, so when it does, we like to use it as much as possible. Alright, so here's an example of the notation. So N meaning it's a normal curve with a mean of 20 and a standard deviation of 5. So if I were to put it on the normal curve, the mean is 20, and that means that every standard deviation I move above or below, I'm going to add 5 or subtract 5. So if I'm 1 standard deviation above, I'd be at 25 because that standard deviation is 5. If I'm 2 standard deviations above the mean, I'm going to be at 30 because 5 and 5 are 10, so that's 10 above the mean of 20. And then if I'm 3 standard deviations, that's 35. And likewise, on the flip side, if I go below, so if the mean is 20, then 1 standard deviation below is going to be 15, 2 standard deviations below is going to be 10, and 3 standard deviations below is going to be 5. And the reason that I chose 3 is because we're going to learn later on, I think in our lesson tomorrow, that almost all the data on a density curve, so 100% of my data is below the curve, but almost all of it is always within 3 standard deviations of the mean, so 3 above or 3 below. And I want to point out one last thing here, that if my mean is here, 50% of my data is below because it's a normal curve, so it's roughly symmetric, meaning the mean and the median are the same, and 50% of my data is above that mean. All right, so go ahead and pause the video. We've talked about, just introduced you to the density curve and the normal distribution. I want you to write down what you think is important, what are you going to need to remember, draw pictures, have an interaction in your notes with the information so far. All right, so let's come back to this problem, my ACT versus an SAT. So we need to do some standardizing, which standardizing is simply converting observations from their original values to a standard deviation unit. So it's taking any number that has it in its context and putting it in a common language. When we standardize data, we convert data points from different sources into one common language, and the reason we do that is to be able to compare the results. So up here, I have a 26 on the ACT and a 1610 on the SAT. Those are two very different scores. So I want to put them into a common language, so I want to standardize those scores in order to compare. We want to see the observed value, so observed value is just what's my score, compared to the other results, so compared to everybody else who took it, and see how it ranks. And that's where we calculate the percentile. So the percentile is the distribution that is below the value of the given observation. So if I'm in the 80th percentile, that means that I did better than 80% of the people who took the test. So the biggest thing to remember, it's always talking about everybody who is lower than me. So my value and the percentile would be everybody below me. So the 80th percentile, I did better than 80% of the people who took the test. If I were in the 4th percentile, that would mean I only did better than 4% of the people who took the test. So percentile puts us in comparison to the others, and specifically comparison to those below us. All right, so let's calculate percentile. So here are the results of an IQ test. So I can see that 2 people did very, very low, scored very low. I had 15 people score low, and so on and so forth, all the way up to very high. So the question is, how did the circled student do? So right here, how did this student do? So I can see they scored high average, but in comparison to everybody else, how did they do? So how many people did he or she outperform? So basically, how many people scored below that student? So we're talking about all these people, these people, these people, and these people. So I'm going to need to add them up. So I see that there are 2 people in this category. And so go ahead and pause the video and count up how many people are in each group. So I see that this student outperformed 65 students. So there are 65 students that did less or scored lower on the IQ test than that circled student. So to find the percentile, I need to know, okay, so she did better than 65, but out of how many total students? So then I need to add up and find out how many total students took the test, including herself. So when I add them up, I see that 99 students took the test. So if she did better than 65 out of the 99, my percentile will come from taking 65 divided by 99, and I get 65.66%. And for percentile, I generally tend to round to the nearest whole, so that would be 66th percentile. So that means that she did better than 66% of the other students who took the test. That's what percentile means. All right, so let's practice with percentile. So below is the distribution of our Chapter 1 test scores, and also the distribution of last year's Chapter 1 test scores. So I want to know who did better compared to the class, a student who got a 63 last year or a student who got a 63 this year. So go ahead and pause the video and think about the things that you're probably going to need to do in order to compare using the idea of percentile. All right, so when I'm calculating percentile, I always need to organize my data first. So if you notice, this is not in order. So the easiest way is to make a stem and leaf plot. So I'm going to make up a stem and leaf plot of our Chapter 1 scores. So I notice that my data goes from the lowest of 20 And I went up to 90s because I'm actually going to compare it to this one, so I wanted to have the 90s because there are some 90s on here, even though my highest is actually 77. So now I'm just going to go through and I'm going to put the single digits, the ones digits, where they fall, and I want to keep them in order. So as I put them in a stem and leaf plot, I put them in order so I can see that I had 2 in the 20s, 4 in the 30s, 4 in the 40s, and so on and so forth. And there are 21 data points here and 21 up here, so I know I did it correctly. So what I need to do next is I need to find how many data points are below the given point, because remember, percentile, we're talking about what is below. So on the previous slide, we asked about a 63. So when I look at this, I had 2 63s in this year's scores. So I want to think about everybody who is below a 63. So if somebody scored the same as me, I'm not outranking them because percentile is everything below. So I'm going to be looking at this 63 right here, and I need to know how many data points are below the given point. So I'm going to count up how many people scored less than me. So 14 people scored less than me. And then how many total data points are there? So how many total people took the test? That's including myself. There were 21 people. So what percent is below the given point? That would be found by taking 14 divided by 21, and I get 66.666667%. So we're just going to go to 67%. So a 63 had 67% of the data below it. So what is the percentile? And how do we interpret that? So a score of a 63 is in the 67th percentile, meaning that score is better than 67% of the class. So go ahead and pause the video, and I'd like you to go through the same process but with last year's Chapter 1 scores and see how a 63 does compared to last year's students. Alright, so hopefully you were able to find that a 63 did better than 3 students out of 20, which is 0.15. So a score of 63 is in the 15th percentile, meaning that that score is better than 15% of the class. So a 67 is in a higher percentile this year, but that's because more people did poorer on the test than last year's students. Alright, so percentile can be easily calculated when I know the raw data. So I saw how many total points, I saw how many did better, how many did worse. But what about a test I don't know the information about? All I know is my score, and I want to know which test I did better. So if I can gather 2 more pieces of information, I'm going to be able to standardize those 2 scores to be able to compare them. Alright, so if I know the mean and the standard deviation, I can then standardize to compare those. So the ACT in 2000 had a mean of 21 and a standard deviation of 4.7, whereas the SAT in 2000 had a mean of 1497 and a standard deviation of 322. So I can see that in both cases, I did better than the mean. But how much better than the mean did I do on which test? And that will tell me which test I did better on. So if we think about it on a bell curve, because we're dealing with normal distributions, I know that the mean on this one was a 21, and the mean on the SAT was a 1497. So I know that my score is going to be somewhere greater than a 21 and somewhere greater than a 1497. So I know that I did better than 50% on both tests because in a normal curve, 50% is above the mean and 50% below. So I know that I'm better than 50% of the people who took the test, but how much better? So in order to standardize the score, in order to compare results, we need to calculate what's called a z-score. So a z-score is a standardized value that tells you how many standard deviations above or below the distribution mean an observation is. So that's really important. Whatever my z-score is, that tells me how many standard deviations I am either above if it's positive or below if it's negative, the mean. So our formula, you're going to need to memorize this. It needs to become your best friend. is it's simply my z-score comes from taking my observed value, so the value that I'm looking at, subtracting the mean, and dividing by the standard deviation. So seeing how far away from the mean it is, that's the subtraction, divided by the measurement that I'm using for that bell curve, which is a standard deviation. So in symbols, it's going to be z equals x, x being my observed value. So if I'm looking at scoring a 26 on the ACT, that's my observed value, minus the mean divided by the standard deviation. And so again, the z-score tells us how many standard deviations a value is from the mean. A negative z-score means I'm that many standard deviations below the mean, and a positive z-score is going to tell me I'm that many standard deviations above the mean. All right, now that I have all the information I need, let's calculate the z-score. So the ACT, I'm going to say z equals my observed minus my mean divided by my standard deviation. So my score on the ACT was a 26 minus the mean, and the mean was a 21. So I did better, so I'll be above the mean, so my z-score should be positive, divided by the standard deviation of 4.7. So 26 minus 21 is going to be 5, and then 5 divided by 4.7 gives me a z-score of 1.06. And we always go 2 decimal places because we're going to learn in our next lesson how to use that z-score on the table A. So that means that I am 1.06. My score of a 26 is 1.06 standard deviations above the mean. So go ahead and pause the video and see if you can determine the z-score for my SAT score. Hopefully you were able to calculate that my z-score on the SAT was a 0.35. So I was 0.35 standard deviations above the mean compared on that one. So if you look down here, I created 2 normal curves, and I compared my scores to the standard deviation. 21, I added the standard deviations each time to get 3 above, and I subtracted that 4.7 to get 3 below. Same here, if my mean is 1497 and my standard deviation is 322, as I add 322 points, I will go above, subtract, go below. So when I graphed my score of a 1610, I'm about a little bit closer to the mean than halfway between the mean and 1 standard deviation, because I'm less than this 1819. So if you look, by taking these 2 scores and standardizing them, or putting them both into something that has a common language, on the ACT, I can tell that I did better because I was 1 and a little bit more standard deviations above the mean, whereas on the SAT, I was only 0.35 standard deviations better. So once I standardize the scores, I can compare the 2 standardized scores, and I can see that because this is a higher z-score, I did better on the ACT. All right, so again, we're looking at our Chapter 1 scores. We're told that the mean is 52 and the standard deviation is 13.9. So we're going to look at 3 different scores and what their z-score would be and what it means. So first, let's start out with the person who scored a 70. So what would the z-score of a person who scored a 70 be, and what does it mean? So go ahead and pause the video and calculate and interpret a z-score for a 70. So hopefully you were able to get that a person who scored a 70 is 1.29 standard deviations above the mean. Now I want to clarify something. We talked about percentile before, and percentile is compared to everybody, like your ranking. So we are going to eventually use the z-score to connect to a percentile, but I don't want you to get those 2 values confused. So right now we're just dealing with the z-score, and that's telling me how many standard deviations above or below the mean I am. Once we move into our next lesson, we'll be able to use that z-score to calculate a percentile. But right now, I know that I'm 50%. I'm above 50% because my mean is the middle number, and when it is my average, and when it's a normal curve, it's symmetric. So half of my data is above and half is below. So if I'm above the mean, I know I'm at least better than 50% of the data. All right, so now I'd like you to calculate the z-score of somebody who scored a 50 and tell me what that means. So hopefully you were able to get negative 0.14. So what that means is that a person who scored a 50 is 0.14 standard deviations below the mean. So they're just barely below the mean because 0.14 is not very far. And if you think about it, that makes sense because a 50 is not that far below a 52 when we're measuring about 14 points apart. So 0.14 standard deviations below the mean is what a score of 50 would be. The last thing we're going to do is we're actually going to talk about how do I work backwards if I'm given a z-score and I want to find out what the observed score is. So this is why we did that practice over the summer with your summer packet on solving some algebra equations backwards. So a highly selective university will only admit students who place at least 2 z-scores above the mean on the ACT. So compared to everybody else who takes the ACT, they will only take people who are at least 2 standard deviations above the mean. And if the mean is 18 and a standard deviation of 6, what is the minimum score? So I'm looking for that observed value in order to be admitted to this university. So let's start with our formula. So the observed value minus the mean over the standard deviation. Well, I know the mean is 18. I know that the standard deviation is 6. And I know I'm looking for 2 z-scores above the mean. So I'm looking for a z-value of 2. So let's go ahead and plug those in where they belong. So z is 2 because I'm looking for 2 z-scores above the mean equals my observed, which that's what I'm actually looking for, the minimum score. So what would this be? Minus 18, because that's the mean, divided by 6, the standard deviation. So how would I get this by itself if I didn't know what it was? So let's go ahead and call that x because we don't know what it is, so let's make it a variable. So x minus 18 over 6, and we want it to equal 2. So now we just have some basic algebra. Let's multiply by 6 to clear out the divided by 6. So I have 12 equals x minus 18. So to solve for x, I'm going to add 18 to both sides. So x equals 30. So in order to even be considered by this university, you need to have an ACT score of 30 because that would be 2 standard deviations above the mean, which is what everybody did. Alright, so go ahead and pause the video and I'd like you to try the second example by yourself. So hopefully you were able to set up that negative 1.5 because he was 1.5 below the mean, standard deviations below the mean, equals x, the score that we're looking for, minus 75, the mean, divided by 8. And as you use your algebra skills, you should have gotten that x is 63. So Andrew's exam score had to have been a 63 if he were 1.5 standard deviations below the mean. So what that means is he did worse than 50% of the class. Alright, so we have made it through our objectives of being able to explain the characteristics of a normal distribution and the importance. We talked about standardizing and we calculated and interpreted z-scores. So go ahead and pause the video. These last two are the ones that we just recently covered. So go ahead and have an interaction in your notes. What are things that you need to remember? What questions do you have? What do you understand? What formula do you need? Go ahead and interact with your notes. And as always, I like to give you all of the vocab with their definitions in one spot. I'll see you tomorrow.